Vectors, here we go. One-dimensional vectors are boring. Let's consider motion in a two-dimensional plane. Because that's really where you're going to need vectors anyway, is when you get into 2 dimensions. And to sort of show you that, I have freed Hal from his one-dimensional prison. And now he is free to roam across the plane. There you go. He could go that way. The vector could have a velocity there. He could go this way, a velocity that way. He could go this way. So clearly now we need not only to describe how fast Hal is going, but what direction he's going to specify the motion. And you do that with a vector. So let's see. First, you can consider 3 ways that you're going to need to be able to represent the vector for his velocity. The first is in a diagram. So we encourage you to always draw diagrams of your problems you're trying to solve, so you can draw all the little forces and velocities and accelerations. So the diagram here would pretty much be a drawing of the table. And here's how here, and the velocity is a vector, and you represent it with an arrow, like that. So the vector is an arrow, and the length of the arrow represents how big the velocity is, how much velocity there is, and the direction, of course, represents the direction. The symbol that you put near the arrow to say what it is the V we use for velocity with a little arrow hat on it. Okay, so the symbol for any vector has an arrow hat, because vectors like to dress up. Okay, and none of this is specific to velocity. This is really any vector. I'm just using velocity as an example. Now, so that's for your diagram. When you do a good diagram for a problem, there should be vectors all over it, lots of arrows. You also have to do it mathematically, and for that, there's 2 ways, and this is what makes vectors confusing, is we often need to jump between the 2 ways to represent it mathematically, and really, I want to show you, it's really just 2 coordinate systems. That's really the difference. So if we want to represent this vector mathematically, one option is to put it at the origin of a polar coordinate system. So there it is again. I'll put its symbol up here this time. And if this is the origin of a polar coordinate system, the angle is always defined counterclockwise from the horizontal axis to the right. Okay? So this would be 0 degrees, and if you come up like that, that's theta, the angle theta. Let's see, so this is the angle from the horizontal axis. Counterclockwise. You got to go the right way. So that's one number, you need theta. The other number is the length. Right? In polar coordinates, you have the angle and you have the radius. It's called the radius in the coordinate system. Here, it's just the length. So the length, like I said, here is the amount of the vector, the amount of the quantity, how fast the velocity is. In vector notation, it's called the magnitude. Okay? And the notation is actually to draw the vector symbol with its hat and everything and put 2 bars around it. So that means the magnitude or length of the vector. So magnitude, in parentheses, I'll put length of the vector. And it's basically the quantity. So 2 numbers are required, angle and magnitude. Sometimes you'll see in a book, these bars bother people. People don't like to see those bars. It doesn't feel like a number for some reason with the bars. So sometimes you'll see the magnitude just given as the symbol without the vector hat. When they leave the vector hat off, that means magnitude. I'm going to try to keep the bars in there all the time, so you'll get used to them. One thing to notice is both these numbers are scalars. Right? It takes 2 scalars to make up a vector. So the magnitude is a scalar because the magnitude doesn't have a direction, it's just the length. It's the whole vector together that has a direction. So a lot of times you'll see your vector specified by a length or a magnitude and a direction. But you can also look at them in Cartesian coordinates. All right? So we take that same vector and we can draw it like that. There's the vector. And we can imagine there's an x-axis this way, horizontal, like there usually is, and a y-axis this way. And then we can basically break this down and say how much of this vector is along the x-axis. So we can draw something like that. That would be how much is along x. And we can draw something like that. That would be how much of it is along y. Right? So then we just label those Vx and Vy. And then, again, it's two scalar numbers. So Vx and Vy are the components of the vector. The xy components. Same thing. Here you needed two scalars to specify the vector. Here you need two scalars to specify the vector. It's really just doing it in different coordinate systems. Okay? So finally, the most important thing that you'll need to be able to do problems is to go between these two. A lot of times in a problem, they'll say, give the final answer in terms of the length and the angle. And when you do the problem, a lot of times you do the problems in components, because physics in x and physics in y you can do independently, often in kinematics and mechanics. But then the last thing you have to do is get back over here. Or it'll start at a problem, a ball shoots this way. The first thing you need to know to do the physics is what component is this way, what component is that way. So there's a lot of back and forth between Cartesian and polar. So let's look at those. So polar to Cartesian. So say you are given this and you want to get that, then you just have to do a little bit of trig and you get the velocity, the Vx component is the magnitude times the cosine of theta. If you're given this theta like this, then you know from your trig, if this makes a right triangle, that the cosine would be Vx, and Vy is the magnitude times the sine of theta. Okay? So no deep mysteries here. I just want you to know how to find those components. And sometimes you want to go the other way. A little less common, perhaps, is you want to say, I've calculated my Cartesian components, and now it's asking me for the magnitude. How do we go from Cartesian to polar? All right, so we have Vx and Vy, now we want to go that way. Well, then the magnitude, you basically get from the Pythagorean theorem. It's Vx squared plus Vy squared. Because if you look at this, if you bring Vy over here, you see you have a right triangle, right? So this squared plus this squared is that squared. So take the square root. And then finally, the last thing you might want to get is theta. So if you want theta, that's the inverse tangent of Vy over Vx. And you say, what the inverse tangent, what? And it's just trig, right? If you're looking for this angle, what's tangent? It's opposite over adjacent, right? SOHCAHTOA. If the tangent of this angle is opposite over adjacent, take the inverse tangent of both sides, and then you have the angle. It's the inverse tangent opposite over adjacent. So this is really what you need for most physics problems, the ability to jump between these coordinate systems in 2 dimensions. That's the main vector work you have to do.